Hi, we are back on our discussion on the electronic nature of atoms. In the first video, we were talking about the different concepts, important events that led to the development of the quantum mechanical model. And we said that in the quantum mechanical model, the electrons are located in specific energy levels, and it gives us an estimate of the likelihood or the probability of finding an electron in a certain region of space. Now, another development found in the quantum mechanical model is that it doesn't talk about orbits anymore. Okay, the energy levels are not thought of as orbits anymore, but as orbitals. So when you say orbitals, these are the region of space, these are regions of space where there is a high probability of finding an electron. Okay, and then these are represented in so many ways, and I'll explain later on. You'll get to know later on why that picture is that way. Okay, and what are 2s or what are 1s orbitals, what are 2p orbitals. Just remember that when you talk about orbitals, these are regions in spaces where there is a high likelihood of finding electrons. Okay. Now we talk about quantum numbers. These are basically solutions to Schrödinger's equations, and they describe the movement and the pathway of electrons in its designated orbital within an atom, okay, or within that space, within that particular volume of space. Each electron has a unique set of quantum numbers. So if you could just imagine, the one electron in hydrogen has a set of quantum numbers of its own. Okay, helium, the two electrons of helium has two sets of quantum numbers which are different from each other. And then as the list grows bigger, for example, we go to higher or to larger atoms, iron, gold, each electron has its own set of quantum numbers, but we will be only focusing on the differentiating electrons' quantum numbers. Okay, so in terms of the periodic table, what we are just looking at are the differentiating electrons that distinguishes one atom from the previous one before it. Okay, from the previous one. If you remember in junior high, there are four quantum numbers. There is a set of four quantum numbers. First one is the principal quantum number, which gives us the distance of the electron from the nucleus. And if you have N, you also have L, which is the angular quantum number, or the azimuthal quantum number, which gives us the shape of the orbital. M stands for magnetic, okay, which tells us the orientation in space, and S is for spin, okay? And then we'll be dealing with them one by one. So the first quantum number is denoted by letter N, okay? It gives us an idea of the principal energy levels, okay? This is the energy level on which the orbital resides. So we think about them as the one we review or we go back to the planetary model. So the N here represents the principal quantum number or the energy levels. So it gives us an idea on the energy associated with an electron. The farther it is from the nucleus, okay, the higher will be its energy. Now, in terms of the principal quantum number, there's a little bit of math there. If you want to find out how many electrons, all in all, are present in, for example, n is equal to 2 or n is equal to 3, then we can just use this equation. The total number of electrons in an energy level is equal to 2n squared, okay, where n is your principal quantum number. So for example, in the first energy level, n is equal to 1. We substitute 1 here, so that's 1 squared times 2. Therefore, in this particular energy level, there are only 2 electrons. However, if you want to find out how many electrons there are all in energy level 2, n is equal to 2, then that is 2 squared, 4 times 2, that's equal to 8. Okay? And then I hope you get to remember this pattern. If n is equal to 3, that's 9 times 2, 18. Okay? So n is denoted by the numbers 1, 2, 3, 4, and so on. The higher the number, the higher the energy. Next one is the azimuthal, or the angular momentum quantum number, which is represented by the longhand letter L. Okay, azimuthal or angular momentum quantum number represented by L, which gives us the subshell. So in the main shells, okay, in the main energy levels, there are also subshells, and we designate those subshells as S, P, D, F. Now, the azimuthal quantum number describes the shape of the subshell in a particular energy level. So, in an energy level, there could be one, or there could be two or more subshells, and we'll get to find that one out later on. Now, always remember that allowed values for L are integers ranging from 0 to n minus 1. Okay, 0 to n minus 1. So if you have n is equal to 2, the allowable values only for your azimuthal are 0 and 1. Okay, because only it's up to n minus 1 lang. Now, this gives us the description, okay, or to what sub-level does the electron belong. So if you have 0, we designate it as S, okay, 1, P, D for 2, and 3 for F. Okay, and then in the module you have there the different meanings. The letters are actually derived from the words, from the descriptors of their spectra. Okay, so you have sharp, principal, diffuse, so on. Okay, and so this is how they look like. In the when you talk about azimuthal quantum numbers, they give us the shape, right? The shape or the type of the subshell. So you have S here, P, and then D is like a clover leaf, and then P is like a dumbbell. F is quite too complicated to represent. Okay, so it has a lot of lobes present. So maybe 30 seconds to answer this question. What are the allowable values of L if n is equal to 1? If your answer is 0, then you are correct. Okay, and then there's the L there, the value represented by L by 0 there is only one sublevel. And what is that sublevel? That is S. So maybe an important mnemonic for this is 0S, S, P, D, F. Okay, S, 0, P is 1, D is 2, F is 3. All right, so for example, what are the allowable values of L if n is equal to 3? Okay, so what are the set of possible values? You have 0, 1, 2. Okay, 0, 1, 2, and these are the 3 sublevels only. Okay, and take note that the number of sublevels is also the main energy level number, the principal quantum number. They are the same. Okay, so 0, 1, 2, and what are these sublevels? Again, S, P, D, F. So 0 is S, 1 is P, 2 is D. Okay, so those are the sublevels present in n is equal to 3. Meaning to say, in the third energy level, in the third orbit, okay, or ana lang ha, because we do not call them orbit anymore. In the third circle, away from the nucleus, you have 3 sublevels. And what are those sublevels? You have S, you have a sphere, you have a dumbbell shaped, and you have a clover leafed shaped sublevel. Okay, the SPD. If n is equal to 4, then you have 0, 1, 2, 3. These are 4 sublevels, and what are those? You have the complete set, the SPDF. All right? So, after identifying the azimuthal quantum number, we also have the magnetic quantum number, which gives us now the orbitals. So, each Sublevel contains one or more orbitals of different orientation. So this is our keyword here. If you talk about magnetic quantum numbers, these are now the orientations of the shape. Okay, for example, the sphere S has a spherical shape. No matter how much you turn it, there's only one orientation, there's only one face. However, if you have the dumbbell, okay, later on, you can either place the dumbbell vertically, horizontally, or going through the plane. Okay, but so much for that. It will be more apparent later on. So just take note that the number of orbitals is equal to 2L plus 1. Okay, so that means the number of orientations is based on the, the quantum number L, or the azimuthal, 2L plus 1. Therefore, if you have a certain number, azimuthal quantum number L is equal to L, then the ML, the magnetic quantum number, the allowable set will be negative L down to the positive L. We'll illustrate this further. So for example, what are the possible values of ML if L is equal to 0? Okay, which is the S sublevel. So another way of putting it is how many orientations are there for the S sublevel? There's only 0. Okay, or there's only one orientation, and we designate that orientation as 0. ML is equal to 0. There is only one orbital for the S sublevel. However, what is the ML if L is equal to 1? Okay, what are the set of allowable values for ML if L is equal to 1? So we start with the negative value of L, negative 1, 0, plus 1. So 3 orbitals for the P sublevel. Okay, meaning the P sublevel, the P subshell has 3 orientations. What are the possible values of ML if L is equal to 2? Okay, so you must get the pattern now. ML is equal to negative 2, negative 1, 0, positive 1, positive 2. So since L is equal to 2 denotes the D sublevel, it describes the D sublevel, then the more orbitals we have. Okay, as for this case, there are 5. So we start from the negative value of L. Negative 2, negative 1, 0, plus 1, plus 2. Okay, now what about M sub L if L is equal to 3? Okay, which is now our F sublevel. Remember, S, P, D, F. So if L is equal to 3, that is our F sublevel. Okay, so where do we start? We start with negative 3, negative 2, negative 1, 0, plus 1, plus 2, plus 3. Okay, and so those are the 7 orbitals, the 7 orientations for the F sublevel. And these are, the following slide shows those pictures or those orientations. Okay, now take note that each orientation, each orbital can only hold up to 2 electrons of opposing spins. Okay, that's a general rule which will be discussed later on, but just for you to know, for each orbital or each orientation of the subshell only has or can only accommodate a maximum of 2 electrons of opposing spins. Say, so if you have the S orbital, it only holds 2 electrons, so it's spherical. Now, so how do we know this? So the value for L for S orbitals is equal to 0. So the more you go up the energy levels, there are also different S orbitals there. So for example, if you have N is equal to 1, there is a sublevel S there. Okay, if N is equal to 2, there is also another S sublevel, so you call it 2S. And the farther away you are from the nucleus, the larger the S sublevel gets. Okay, they are spherical in shape, and the radius of the sphere increases with the value of N. Okay, and this is just a graphical representation. So again, we are talking about the probability. So observing a graph of probabilities of finding an electron versus the distance of the nucleus, we see that s orbitals possess n minus 1 nodes, or regions where there is zero probability of finding an electron. Okay, so for example, in the first graph, there is a distance from the nucleus where there is highest. Okay, so you look at the x-axis and you look at the y-axis. So at a certain distance, let's say here, it's more or less at 1, there is a high probability of finding an electron there in the s sublevel. Now, the second graph actually tells us two s sublevels in an atom. Okay, so at this area there is a high probability, and then in here there is also a high probability, and it will be shown later on what this means. Why are there zero values? Why are there no values? Okay, this represents the peak area man, the peak area where there are where there are electrons. So here, okay, if you try to study the graph, there are areas that are white. Okay, that means there is no chance of finding electrons there. There is a node. Okay, the probability represented by psi to us here, the Greek letter psi. Okay, and then there are areas in the graph which are actually zero. Okay, so meaning in these areas, if you get the cross section, okay, or you think of it as an onion, there are no electrons that can be found there. So the height of the graph indicates the density of the dots as we move from origin. All right. So there are areas which have uh, no electrons, and take note that we are comparing now the s sublevels for the main energy level. So for example, in energy level number 1, there is a 1s. Okay, but in energy level number 2, there are two s orbitals, 1s and 2s. So this is your 1s, this is your 2s, the second, and so on. All right. Now let's go to the p sublevel. The p sublevel holds up to 6 electrons. Okay, so if you remember, this is there are, if you go back to the magnetic quantum number, we said that if you have P, S, P, D, F, so S is 1, so what are the allowable values? You have -1, 0, plus 1. There are 3 orientations, and we can think of it as this way, -1, 0, plus 1. I'll show the summary later on. Okay, so these are now the pictures of the orbitals. So this is the p orbital lying along the x-axis. This is the p orbital lying along the y. Okay, this is the pz orbital. And if you look at the whole sublevel, if you combine them, you get this, right? The d sublevel, it gets more or less complicated here, but the atoms, or the electrons rather, are moving along that shape, okay, the cloverleaf shape. Okay, and there are different orientations, just like that what we've shown. But remember that the d sublevel holds up to 10 electrons. Okay, the d can hold up to, and 10, only sublevel the d sublevel holds up to 10 electrons. Okay, and then these are your orientations. Now the f orbitals, okay, remember that the f, s, p, d, f. So we start with -3, -2, -1, 0, plus 1, plus 2, plus 3. So there are 7 allowable orientations, 7 orbitals. And these are now those orbitals, or these are now your orientations. Okay, and it gets a little bit more complicated here. Okay, and this is now our maybe summary. And if you try to look at, these are the ML numbers. Okay, the magnetic quantum numbers. For S, you can just have 0. Okay, 0, but for P you have negative 1, 0, positive 1. For D, negative 2, negative 1, 0, plus 1, plus 2, so on and so forth. Okay? So, if you tabulate these, if you tabulate that information, we can have energy level and the sublevels, and then the type of sublevel, so the number of sublevels. So notice that the number of sublevels is the same with the energy level to where it belongs. So for example, in energy level number 1, okay, remember the planetary drawing? In the first circle there is one sublevel which is S. Okay? In the second circle, in the second larger circle, there are two sublevels which are S and P. Okay? And as the number of the energy level increases, the number of sublevels also increases. That means at main energy level number 3, there are SPD sublevels. Okay? And then you have this, right? So the type of sublevel, you are given there the shape, okay? And then you are given the number of orientations, which gives us the number of orbitals, okay? So 3, 5, we discussed this a while ago na, and then the total number of electrons in the sublevel, okay? So if you get the total now, if you get the total, you have energy level N, okay? And then remember that we have this equation, okay? So we can just use this equation to predict how many electrons there are. So 2 in the second energy level, 2, there are two sublevels which are S and P. S can accommodate 2 electrons, P can accommodate 6 electrons. So the total number of electrons present in that energy level is 8, the maximum. Okay, the maximum number of electrons is 8. In energy level number 3, you have 3 sublevels. One is S, which can hold 2 maximum electrons. Another is P, which can hold a maximum of 6 electrons. Okay, because there are 3 orientations, so 3 times 2. And then you have D, okay, 5 orientations times 2 electrons, you get 10. So if you add them all up, you have 2 plus 6 plus 10 is equal to 18. Okay, for the third energy level only. In the fourth, you have SPDF, so you have 32. Okay, the same principle. Take a pause first, and then if there is something you'd like to have rewinded, so you can rewind, you just look at the pattern. Okay, next. We had initially discussed the 3 main quantum numbers, but there is a more recent one, okay, a relatively recent one. Electrons in the same orbital do not have exactly the same energy. And why is that? If you have a beam of atoms here and you let them through a slit and you let a magnetic field interact with them, they found out that uh, for two atoms, two adjacent atoms in the periodic table, one is deflected and then another to the right, or one is deflected to the left, so different deflections. So what they actually know is that they concluded that there must be something that differentiates them. Okay, and what is that something that differentiates those two electrons that are next to each other in the periodic table is its spin, the spin of the differentiating electron. Okay, so the spin of an electron describes its magnetic field, which affects its energy. Okay, so if your electron turns clockwise, we draw an arrow up, okay, and then if it's counterclockwise, an arrow down. So that experiment led to a fourth quantum number, which is ms, and it has only two values, plus 1/2 and negative 1/2. So if the electron is pointed upward, okay, it's spinning clockwise, That's positive 1/2. If it's counterclockwise here, negative 1/2. Okay, and that is the basis for the arrows in the orbital diagrams. Okay, so there's one. Some people would like to have a half arrow, okay, while others use a full arrow, but doesn't matter as long as we know that they are the electron spins. Now we'll go to these later on, but just uh, an extension. We usually draw orbital diagrams for specific atoms in the periodic table. So an orbital diagram consists of a box or maybe even a line representing each orbital and an arrow representing each electron. The spin of an electron represented by the direction of the arrow is often referred to as either spin up or spin down, and there must only be two electrons in an orbital, and they must have opposing spins to counteract the force of repulsion. Okay? So in terms of energy, okay, for one electron hydrogen atom, they found out that the same energy levels have the same energy. So those orbitals who know that are found the in the same energy level, such as this one, and is equal to 2, na kay 2s and 2p, they have the same energy. But that only works for hydrogen, okay? Because there is only one electron. There is no other repulsion from the other electrons. Now, electrons or orbitals having the same energy, we consider them to be degenerate. Okay, remember the term, degenerate. Now, what about the multi-electron atoms? So as the number of electrons increases, so does the repulsion between them. Okay, so there is repulsion among the electrons in the same energy level, such that in many electron atoms, the same energy level are no longer degenerate. Okay, so you noticed a while ago, tapad C2s o C2p. However, because of the repulsion, those electrons belonging to 2p actually have higher energy than that in 2s. Okay, and this is the basis later on for the electron configuration, the Aufbau principle. There are differences in energy for the orbitals belonging to the same energy level. Okay, and so you have this. So it lists the orbitals from lowest energy to highest energy. So you have 1s, 2s, 2p, 3s, 3p, going upward 4s. And they found out that 4s has lower energy than 3d, okay? And 3d has lower energy than 4p. So the energies of the orbitals or of the electrons present in these orbitals are arranged according to from lowest to highest. All right. And so this is a prelude now to the discussion in electron configurations. Just a few more slides. I'd like to connect the discussion from the first part to here lang. Okay, so going back, how is this relevant? In electron configurations, these are actually the result of studying the quantum numbers. So here, this shows the distribution of electrons in an atom. So each component or each term in the electron configuration has a number denoting the energy level. So this is 4, okay? Meaning ang dako nga 4, the coefficient 4 tells us that that electron is present in the main energy level number 4. The n is equal to 4. A letter denoting the type of orbital, p, okay, and a superscript denoting the number of electrons in those orbitals. So 4p5. Okay, so that is where the the quantum numbers come in. And we also take note that the periodic table is arranged in such a way that it after the quantum numbers that can reflect the different quantum numbers. So we fill in orbitals in increasing order of energy. So for example, if you have hydrogen which has only one electron, it belongs to 1s here. Okay. and then it reflects now. This is your S block. This will be a useful tool later on. This is the P block. Okay, take note that S has two cells in the periodic table, okay, representing those two electrons, the maximum of two electrons that the S orbital can hold. Okay, the P block here, the P block has 1, 2, 3, 4, 5, 6 cells in the periodic table. So those 6 cells represent the maximum number of electrons that the P sublevel can hold. All right. The D has how many? It should be 10. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, representing the maximum of 10 electrons that a D sublevel can hold. And of course, you know what happens to F. Okay. Now, our next lesson is actually on the periodic table, and then we will delve in the electron configuration before the periodic table, and we'll delve in to this more. Okay, so different blocks on the periodic table shaded in different colors correspond to different types of orbitals. Okay, so that's it for now. Okay, and as I said, differentiating electrons of an element is what distinguishes an element from the one before it. Okay, and this is the last electron in the orbital diagram. And you have this. Okay, so we'll end here. There will be a separate discussion on electron configuration. But for now, I'd like you to go back to your module and to identify the laws on uh, how to fill out or to fill in the different levels. Okay, there are actually three, and then we can use it as a springboard for our discussion. And late in the next few meetings, we will be relating everything in here to electron configuration, to reactivity, and to the other chemistry concepts. All right? So I hope you have a grand day ahead of you, a grand week, and enjoy the rest of the day.